We're going to try to make it through example 6 with this, and we're just looking at rational root theorem. Our Descartes' rule of signs will play into that, but right now we just want to make sure that you can find all the possible rational roots. So that's one question, one thing you'll be asked. And by finding the possible rational roots, we want you to find the roots, the actual roots, using synthetic division. So let's take a look at what that looks like. If you look through your rational root notes, example 1 is a problem just like we've been doing. It's something that you can factor. So I've already done that for us. I factored out a negative, and then that trinomial actually factored with trial and error. And I can finish this up. That'll be x minus 3, x plus 3. And I know if I set each piece then equal to 0, that this x squared plus 2, when I set that equal to 0, I'm going to get x squared equals a negative 2 and try to take the square root. These are going to be complex or imaginary. So these are not going to be real, non-real. So I don't have to worry about putting those on my graph. When I set these pieces equal to 0, then I'll wind up with 3, 0, which is already on my graph, and negative 3, 0, again on the graph, and each of those have a multiplicity of 1. I also went ahead and found my y-intercept, and I know by looking at the standard form, it's a 4th degree, and it is negative, with that negative in front. So what that tells me is that both ends are going to point down, remember, right? And this is going to go way up here. I've estimated 18 to be up here somewhere. It's not exact, but it's up there in the air somewhere. And your graph's going to look like an upside down parabola. The imaginary roots will do some other things to it, but for our purposes, that's what your graph should look like. When you look at example 2, this one, it will not factor, not even by grouping. You could try if you'd like, but they told us already what one root is, so even if it would group, I would use the root they gave me. So I'm going to take this x minus 1, or x equals 1, all right, and I'm going to do my synthetic division to reduce that. So I'll pull the 2 down. 2 times 1 is 2. That gives me 13. 13 times 1 is 13. That gives me a 6 when I combine it with negative 7. 6 times 1 is 6. And 6 minus 6 is indeed 0. Gives you a remainder of 0. You knew it should because you knew you were dividing by something that was a root. What that tells me, though, is, remember, you reduce the power by 1, so this is 2x squared plus 13x plus 6. This trinomial multiplies by the factor that gives you x equals 1, so that would be x minus 1, in order to equal my dividend. So what I've done is I've factored that partially. I can continue to factor that because that would be 2x and x. And in order to get the 13, I'll do 6 and 1, both positive. So there's 12x and 1x, which is the 13. So this is my function, right, equals this, my original dividend. And in order to graph now, I just set the whole function equal to 0. So each piece equals 0. We get 1, 0. We get a negative 1/2, 0. And we get a negative 6, 0. Putting each of those on the graph. Negative 1/2. There's 1, 2, 3, 4, 5, 6. It is cubic and it's positive, so we know the left side should be going down, the right side should be going up. We have a y-intercept of negative 6. And each one of those has a multiplicity of 1. So with a multiplicity of 1, we know it's going to cross. So it goes up and back down and back up, and it'll continue going up. Should look something like that. Again, I really just used a root that I was given in order to use synthetic division to find another factor. Right? So looking at example 3, when I look at this one, I can't factor that straight up. It doesn't have a common factor. It is, although it's a trinomial, it's an odd power, so I can't do trial and error. I can really can't do any type of factoring. So the only thing I could do is start guessing roots, right? If they tell me a root, then that's awesome. You know, as you see down here, what if I told you x equals 6 is a root? Well, if you tell us that, then what we can do is we can actually use synthetic division then, just like we did on number 2. So we'll bring our 1 down. That's 6. 6 times 6, 36, which is 6, 9 is 54. So indeed it is a root, and that gives me x, reduce your power by 1, so since this was cubed, that's squared, plus 6x plus 9, and the x equals 6 gives me a root, that is a root. It gives me a factor of x minus 6 to equal my function. Right? Those two multiply together to give me the original function, and I can factor. You may recognize that as a perfect square trinomial. If not, you can do trial and error, and you would get x plus 3. But if you recognize right off, it is x plus 3 squared. We'll bring the x minus 6 down. And at that point, since this is our function, we'll set the function equal to 0. We'll set each factor then equal to 0 to find the roots, and we'll get 6, 0, negative 3, 0. Negative 3 has a multiplicity of 2, which tells me it bounces. Whoops, off the screen, sorry. And 6 has a multiplicity of 1, which means it crosses. If you look way back up at your standard formula, when you plug in 0, you know that your y-intercept is going to be 0, negative 54, so it's going to be way down off the graph. 1, 2, 3, 4, 5, 6. Putting these on here. It's cubic, so you know it acts like a line, and it's positive, so it's a positive slope line, so the left side's going down. It bounces at that negative 3, so it comes and does this and bounces way down to negative 54 somewhere, turns back up, and it goes across. So our negative 54, apparently, we're just saying, is down here. All right? That's what example 3 should look like. Again, in this case, they gave me the root. They told me that x equals 6 was a root. What we need to do is decide how we can find roots. So if you look on in your notes, there's a few little facts you need to know. It tells you that polynomials are easy to factor with synthetic division. That's what we're doing, is we're using synthetic division to factor. Right? All polynomials, every single thing we give you, all polynomials will factor to be either linear factors or those irreducible quadratics. Remember, irreducible quadratics mainly come from cubes, which gives you imaginary, but you could get irrational roots as well out of those. But it's some quadratic that you can't factor, knowing what you know. What if we're not told a particular root? Well, that's where rational root theorem comes into play. Rational, because we're getting rational numbers, rational root theorem gives us choices. All right. How do we know what roots to use? Well, rational root. And that creates an educated guess. So you're not just starting, oh, I'll divide by 1, I'll divide by 2, I'll divide by 3, and so forth. You're going to make a list of all the possible choices and then choose from that. All right? So if you take a look, continue on, we use that rational root theorem. And the definition is, rational root theorem gives us all the possible these were supposed to be highlighted, not marked out, but possible rational roots. Possible rational roots. All right? Not all the possible roots, because you could have irrational numbers, like square root of 3, or you could have complex or imaginary solutions. All right, here's the way that it works. Rational root theorem creates a list based on the leading coefficient and the constant. Notice it's a constant at the end. It has to not have an x with it. And you're going to hear us refer to this as P's and Q's. P comes from the end, Q comes from the beginning. And we make a fraction of those by P over Q. That gives us all the possible rational roots. So look on example 4, and we're going to make these lists first. We may or may not actually graph them. Make sure that you do not have an x at the end. Whoops. If you have an x with your last term, you're going to have a greatest common factor of x, so you'll factor that out first. This one does not, so our P value is going to be 6. Our Q value is at the beginning, and that's going to be a 1. We're really not worried about the signs on these because as we create this list, we're looking at both positive and negative. So our P over Q, well, actually, let's break 6 down first. What are possible factors of 6? Anything that would divide into it. So I know I could do a positive and a negative. 1, 2, 3, 4 won't go into it, 5 won't go into it, but 6 will. So all those would be factors of 6. 1's nice, because the only thing that goes into 1 is 1. So for our P over Q, all the possible roots are going to be both positive and negative, and then we put each of these numbers over each of the Q values. Well, there's only 1 for Q. So we get 1 over 1, 2 over 1, 3 over 1, and 6 over 1, which are all going to be whole numbers. Look on at example 5. On example 5, it has a greatest common factor of x. So I'm going to start off by pulling that out. So I'll get, and I'm going to take the negative at the beginning too. So I'll get a negative x, and I'll have now x cubed minus 4x squared plus x plus 6. Again, the signs are really irrelevant as far as our P's and Q's. P's at the end, so that's 6. Again, we know factors are 1, 2, 3, and 6, both positive and negative. And our Q's at the beginning, so that's just a 1. And we'll go through, we'll get the exact same list. Let's go ahead and look at number 6, because it is different. If you look at 6, you could possibly see there's a greatest common factor, not of x, but 2. So if we pull that out, actually, let's not do that. Let's leave it as is. This can be our P, this could be our Q, because we do want to get all these possible. So you're only doing a greatest common factor if there's an x involved. So our P value is 48, and there are tons of factors of that. 1, 2, 3, 4, 5's the first number that won't go into it. 6 will, 7 won't, but 8 will. And then we can make pairs if you notice, because 6 times 8 is 48. So 4 will go into it 12 times, 3 will go into it 16 times, 24, and 48. Right? Q, on the other hand, is our 2, so that's just a 1 and a 2. Those are our only things. So our list, P over Q, is going to be all the possible, positive and negative. Each one of these over 1. So I get 1, 2, 3, 4, 6, 8, 12, 16, 24, and 48. But I also have to put each one over 2, so I'll get 1/2, plus and minus 1/2. 2 over 2 is 1, which is already there, but 3 over 2 is not there. 4 over 2 is 2, 6 over 2 is 3, 8 over 2 is 4. All the way up, the rest of these are going to be there. So as you're making your educated guesses, you're going to be picking from this list, which means 1/2 might be an option for you, or 3/2.